machine learning streamflow modeling. I work with Bart Hernán from my department and with Nicolette and Scott from the Science Institute. Okay, so to start with the study area, it is located in Uruguay because I'm from Uruguay. For those that don't know where Uruguay is, it's in South America between Argentina and Brazil. As a little bit about the climate of Uruguay, we have an annual rainfall of about 1,300 millimeters per year. We have rain in every season, but a little bit more on fall and winter. And precipitation could be in the form of snow or rain. In Uruguay, we don't have any precipitation in the form of snow, just rain. And why Uruguay is a good case study for this project is because we don't have a lot of hydrological data available. So it's a good case study to see how to simulate streamflow in these cases. So this is Uruguay, and in red we can see the Rio Negro basin. The Rio Negro flows from Brazil to the limit between Argentina and Uruguay. And in the image, you can see a lot of blue dots. Those are upstream gauges, upstream of the dams. There are the 3 ones in yellow. And then the other gauges are downstream the dams. So here we can see the Rincón del Bonete Dam, which is the first one that the river faces. Then we have the Baigorria one, and finally the Constitución one. As a little bit of context, Uruguay relies heavily on hydropower. 3 of the 4 dams are in the Rio Negro basin. So this is why it's very important to have accurate streamflow modeling, so we can optimize dam operations and ensure energy reliability. Machine learning approaches, specifically LSTM networks, have emerged as a leading approach to model streamflow because of their capacity to store long-term memory. These networks require a lot of data to train, basically because if we have the more basins that we have, then the more hydrological diversity we will have, and then our model will generalize better. Again, this kind of networks require a lot of data. One of those datasets is called CARAVAN. Right now, it covers about 16,000 basins globally. I'm going to introduce this dataset later. However, CARAVAN is based on reanalysis data, so it has been shown that compared to local higher quality datasets, its performance is worse. So the objective of about the objectives of this project. So in this figure, we can see some sub-basins in the Rio Negro basin. Here there are 16, then I subset them to 11 because of data quality requirements. But the idea is to basically train LSTM models across these 11 sub-basins that have, again, limited gauge data. For this, I will characterize 4 different precipitation products: CARAVAN, MSWEP, CHIRPS, and gauge-based products. For this, my approach will be first to do a study on some US basins. Basically, this is why, this is because, sorry, in the US, there is high quality data set based on purely gauge measurements that I'm going to introduce later too. And then with this learning that I have for the US basins, I'm going to translate that knowledge to Uruguay. Finally, my 2 last objectives are to see how the choice of the precipitation product influences the model performance, and also how it influences some hydrological signatures. So let's start with the data and methods section. First, I'm going to introduce the LSTM networks. So LSTM stands for long short-term memory, and these networks are neural networks that include dedicated cells to store memory. This is very useful for hydrological systems because hydrological systems itself store a lot of memory. When we have precipitation, snow or rain, it goes to different storages, as it could be the snowpack. It also could be absorbed by the soil. So that precipitation doesn't go directly into the stream flow. So it could take hours, days, months. So that's why these networks are very useful for hydrology. To explain a little bit about LSTM networks, they receive an input vector that has dynamic and static features concatenated. Dynamic features are basically time series, as they could be precipitation, temperature, radiation. And the static features are some constants for each basin. So these constants work kind of an identifier for that basin. And this is, sorry, I forgot to say, these constants are also let the network exchange information between the basins, and that's why it's so important to have them. So the network keeps two internal states. One is the hidden state that store short-term memory, and this short-term memory is useful to pass information between time steps during the training process. And then we have the cell state that is this very important long-term memory. This cell state is updated by different mechanisms. One is the forget gate that discards information that's not useful anymore. Input gate incorporates new information to the network. And finally, the output gate is what controls which information is passed as a hidden state. Each gate has its own learnable parameters. Those are the weights that characterize our model. To train these networks, I worked with open source Python library called neurohydrology, which was developed to do deep learning research in hydrology. It provides many pre-built LSTM's architectures, but also it provides with pre-built metrics, also tools for parallel computing. And the experiments are defined through a configuration file where you decide on the different hyperparameters, the training and validation periods, and more settings for the LSTM. So here's an example of how a configuration file looks like for neurohydrology. So here we can see the training and validation periods. Some metrics are defined. You can also pick which dynamic inputs and static inputs you can use. You can decide on the loss function. In this case, I'm using the NSC. I'm introducing it later, but also the metrics to evaluate the performance of the simulations, and some hyperparameters, as they could be the batch size, the hidden state, the learning rate. One very important one that I wanted to mention is the length of the input sequence. So basically, this is how many days of information we are feeding into the network. In this case, it's set to 270 days. That's almost 9 months. And this is where we can see like the memory of hydrological systems. So we need a lot of days to make one prediction. Now, when it comes about the inputs, again, here are my basins that I'm using to this study. And some of the time series that I used to my project that are the dynamic inputs are precipitation, the maximum and the minimum air temperature for 1 day, and the radiation. So these time series are a spatial average over the basin. So for each basin, we have one value per day. And then we have the static catchment attributes that are these identifiers that I mentioned. Some of them could be the slope, the elevation, the area of the catchment, also different fractions in the soil, as it could be the sand, silt, or clay. This is what it's very useful to exchange information between basins. Where did I train these models? So I had Azure credits available for this project. Thanks to sponsorship from the Microsoft AI for Good Lab. So all my experiments were run on Azure. I didn't have any experience on cloud computing before, so here Scott and Nicoleta helped me a lot with the accelerator program. And they introduced me to SkyPilot, which is an open source framework that lets you run, in this case, machine learning workloads on any cloud provider. It abstracts away the complexity of setting a virtual machine in a cloud environment. which I was not related with. The benefits that this has is that lets you run your jobs in any cloud provider without changing any of your code. It automatically picks the cheapest option for your needs. Again, in this case, we set a virtual machine to run interactive jobs with a GPU. So basically, I worked with Jupyter notebooks. And for this, we have also to create a new configuration file. Here you can decide on the requirements for your virtual machine. You can also decide to save your outputs in a separate memory from your virtual machine, so they not depend on that. And also, for example, you can set a policy of automatically stopping the virtual machine after, in my case, 10 minutes without any jobs running, so it don't keeps on running and then costing you money. Now, let's start with the datasets. So I mentioned that for the US, we have one high-quality dataset based on gauge measurements, and that's CAMELS. CAMELS stands for Catchment Attributes and Meteorology for Large Sample Studies. So this dataset was developed by the NCAR and includes almost 700 basins over the US. These basins were selected because of being largely natural, but also because they have a long record of measurements. This dataset includes the type of information that I need to train my networks. And all the time series here are the result of interpolating and extrapolating ground-based observations, and that's why this is very helpful, and it works really good. The problem that this dataset was having is that it was also developed for other countries, such as Brazil, Australia, Chile, but the problem was that they were not standardized, so they were using all different sources for their information. So this is how CARAVAN emerges. The name makes a reference to a series of camels. So the idea of this dataset is to standardize the information across these datasets. And now it has data available for almost 16,000 catchments globally. And again, they provide the same information, but now standardized and using the same sources. What's interesting about CARAVAN 2 is that it provides code to extend these datasets to new places. And this is how I extended this kind of datasets for Uruguay. The only thing that you have to provide is a shapefile for your basin and a record of Streamflow, and then you can derive all the other information. So I'm going to make a synthesis of all the products that I'm using. So starting with CAMELS, a gauge-based product developed for the US with a really high spatial resolution. Then for Uruguay, I don't have this data set based on gauge measurements, but I have single location gauge measurements for Uruguay. So I'm also talking about this later. Finally, I'm using CARAVAN, which is a data set based on reanalysis products. So basically, they are outputs of numerical modeling. It is based on ERA5 blend. And then we have MSWEP, which is and CHIRPS. There are data sets that use reanalysis data, but also they introduce satellite information and gauge observations around the world. So now let's go to the results section. For this first, I have to introduce which metrics I'm going to use to evaluate my simulations. Starting with the NSE, which is also my loss function. The NSE measures how good are the simulations when compared to the mean of the observations. So the baseline here is the mean of the observations. We want this value to be as close to 1 as possible, but also I'm using the root mean square error and the mean square error. The advantage of the RMSE is that it's in the same units as the objective variable, that it's the Streamflow in this case. And we want both of these metrics to be as close to 0 as possible. And finally, the mean ratio, which is the mean of the simulations divided by the mean of the observations. We want this ratio to be as close to 1 as possible. Apart from this, as you can see, we use a lot of metrics in hydrology. We also use some specific metrics for the peaks of a hydrograph. A hydrograph is this plot of streamflow over time. Here you can see in orange the simulations and in blue the observations. And the peaks of each time series is flagged with a circle and a triangle. So we have metrics to compare the peaks in the simulations and the observations. First, we have the peak mean absolute percentage error. So this basically compares the magnitude of the peaks. Then we have the peak timing error, which basically looks at how distant in time are these peaks. And then the missed peaks fractions. This fraction is the fraction of peaks that the simulation can't reproduce from the observations. Finally, we look at 3 more hydrological signatures. For this, I have to introduce this plot that's a flow duration curve. So to construct a flow duration curve, you have to have your record of streamflow and then rank them from your lowest to your highest. And that's why it's in the y-axis. And in the x-axis, we have the probability of exceeding that value. So as you can see, for low flows, the probability of exceeding that value is really high because we have a wide range of streamflow values that are bigger than that value. But for lower flows, for higher flows, that probability is much less. Then we look at the 3 sections of the hydrograph: high flows, mid flows, and low flows, and basically compute a bias for each section of the hydrograph. Those are basically the last 3 metrics. So now we can start looking at the results. So our first approach was to use transfer learning by pre-training on a large data set, because we were thinking that having more basins, then we will generalize better for the Uruguayan basins. So we used more than 500 basins for the US and 11 basins from Uruguay, my target basins. Then fine-tune the pre-trained model to only the Uruguayan basins. But the problem that we were having is that the predictions were really bad. And here we can see some examples. So as you can see, we have a lot of missed peaks, really high biases on the magnitude of the peaks too. And this was the case for many of the basins that we were trying to fine-tune the model for. Here are more examples. So we are missing a lot of peaks. Here we have the median metrics for those 11 basins. And as you can see, the NSC is really close to 0. That means that it's almost the same to use the mean of the observations to make predictions, which is really bad. And also the ratio of the means is a lot. So it's really big. So here we are over predicting almost by a 40% our observations. So then we thought about just training for the Uruguayan basins to see what happens. And still, this was the case. We were missing a lot of peaks, over predicting some of them by a lot, as well as under predicting. The timing is not good too. So this was looking very bad. Again, we have the median metrics for the Uruguayan basins. The NSC improved a bit, also the mean ratio, but still we are far from what we wanted to see. So now we are gonna see what happens with the precipitation products, and then I'm gonna start by looking at the US basins. So there are a couple of studies that have demonstrated that when switching from CAMUS forcings, that means gauge-based forcings, to CARAVAN, which are reanalysis products, the NSC distribution drops. So here we can see the distribution in this color map. And then when we switch, this is for CAMUS, and when we switch to CARAVAN, we see a huge drop in the Midwest and on the southern United States. Here we have a plot for the difference of the NSC, and as you can see, that is the region that is most affected by switching these forcings. So to study what's different between the precipitation datasets, we are gonna just focus on a subset of the US basins. This subset was made by picking just the ones that have a bigger difference than 0.2 in NSE, and also the ones that do not have any snow as precipitation, because those are the most similar to Uruguay. So let's start looking at one specific sample, and that example is where we see the highest drop in NSE. And as you can see, if we compare the cumulative precipitation, we see some difference, but it's not huge. So we think that that is not why our hydrographs are so bad. Then if we look at a precipitation duration curve, an idea analogous to a streamflow duration curve, then we see that for MSWEP and for CARAVAN, I think, yes, we see a wider range of lower values, which is one thing worth keeping in mind. So in this case, the range of values for CARAVAN and MSWEP are very similar, and then this is also the case for camels and CHIRPS. Then if we look at how long are the periods where we don't have any snow and plot a hydrograph to see the frequency of that of those periods, we see that for CARAVAN we have a higher frequency on having shorter periods without rain. But then if we look at CARAVAN and MSWEP, sorry, camels and CHIRPS, those periods are longer. So we see higher frequency for longer periods without any rain. MSWEP is kind of in a midway. And then lastly, if we look at this color map, so this color map, what's trying to show is the timing of high and low precipitation. So to build this, what we did is for our period of study, we took the mean for 1 day of the year for the whole record. So we have a time series for 1 year, basically, with median values. And as you can see, for maybe it's not shown very good because of the colors, but for camels and CHIRPS, we see a higher frequency of 0 precipitation, and they are very similar in timing. But for MSWEP and CARAVAN, we have a wider range of low precipitation values. So this is a specific case study, but what happens when we switch to the general case for the US? So here we see in camels in orange, CHIRPS in red, and MSWEP in red. We see that the bias of the total precipitation is not that large. This is the same case as for the specific case that we just saw. This is also the case for the higher precipitation values. This is what's showing this figure. But then if we look at the mean length, if we compare the mean length of those dry periods, we see that those periods are longer for the 3 data sets when compared to CARAVAN. This is one thing that it's worth also keep in mind. And the last 2 plots, what I'm trying to show, and I'm going back to this slide for a little bit. So basically, we calculated the correlation between the median time series for the precipitation. We compare all of them to CARAVAN. So this was to see if the timing of the precipitation is similar or not between the data sets. So now if we go back again to this, we see that that timing is very different for the median values and for the mean values. Now, how does this translate when training a model? So as a baseline for the US, we have the CAMES dataset, which is this gauge-based dataset. And this gave us the best NSE distribution. When we switch to CARAVAN, we see this huge drop. But then when we change the precipitation forcing to CHIRPS and MSWEP, we see a huge improvement. And MSWEP actually approximates a lot to CAMES, which is very important. But also when we combine CHIRPS and MSWEP, we see a really good performance in NSE. Now, what happens with the hydrological signatures that I introduced? So if we look at the timing signatures, we see that across the the models that were trained just with one precipitation forcing, we see that is the one that works best across the metrics for the peaks. CARAVAN is the one that shows the worst metrics when it's about the peaks. And also we see that, combining CHIRPS and MSWEP, it's a good approach. It's important to see this because if now we switch to the bias metrics, we see that actually working with the combination of CHIRPS and MSWEP improves the biases when it's compared to just be training our model with MSWEP. So now, what are the conclusions for the US basin that we are then using to apply in Uruguay? So switching the precipitation from CAMOS to the other datasets impacts a lot the model performance. Despite being similar in precipitation volumes, we see huge difference in the length of those dry periods, but also in the timing of precipitation, which is the key difference between datasets. Among the single trained models, the one that was trained just with MSWEP is the one that performs the best across most of the metrics, but also combining CHIRPS and MSWEP seems to be giving the best results with global-based products. So now, what happens with places that have poorer data quality? So this is the case for Uruguay, and we don't have this CAMOS dataset. So what I've done for Uruguay is to look at the precipitation stations that we have, and to build this time series of gauge-based observations, what I did was, if one gauge fell into the limits of one basin, then I took that time series as representative for all my basin. If more than one fell in the basin, then I took the mean of those measurements. But if that basin did not have any gauges, I took the closest one. This is a huge approximation, but then we are going to see if this helps or not. So now, what's the general case for the Uruguayan basins? As you can see, still the total precipitation bias is not that far from 1, so it's less than 10%. So that's not too alarming for us. But again, when we look at the length of these periods without any rain, we see that those periods are larger for the 3 datasets when compared to CARAVAN. And also the correlation, so the timing of the precipitation is really different to CARAVAN. So now, how this translates when training models for Uruguay. Here we don't have CAMOS, so our baseline is CARAVAN. And when we compare it to CHIRPS and MSWEP, that is the one that we saw for the US that actually worked pretty good, we see a huge improvement when switching the precipitation forcing. The best median NSC was shown when we used all the precipitation products that we have, but again, the median for the option with for training just with CHIRPS and MSWEP, it's really close to that. So now, what happens with the hydrological signatures? As you can see, the gauges are the ones that have the best results when it's about the peaks. So the peak timing is the best for gauges and also the miss-peak ratio. This makes sense because this is real measurements, so they are very correlated to the streamflow measurements. But when we see the bias for the peaks, we see that the gauge is not the one that performs the best. Here, MSWEP actually performs a little bit better. But also, if we combine MSWEP and CHIRPS with the gauges, we see that those metrics still look really good. Now, if we go to the biases for the different sections of the hydrograph, we see that here the gauges do not work very well. And this, again, makes sense because we are making a huge approximation on taking just 1 or 2 sites to represent the whole basin. So in this case, MSWEP performs a little bit better than the gauges. But when we look at the option that used CHIRPS and MSWEP, that was this model that worked really well for the US, with these approximations for precipitation from the gauges, we see a huge improvement on the biases for the different range of streamflow values. So now, how our hydrographs have improved. So here we have the based hydrographs. This was are the results by just training with CARAVAN. And when we switch to the one that was trained with CHIRPS, MSWEP, and gauges, we see a huge improvement. So I can go back again. As you can see here, we were missing a huge peak, and we were over-predicting the low flows, but then our simulations are much better now. The peak has a really low bias. In magnitude, when here, for example, we look at the lower values of streamflow, we see that we are over-predicting most of them. Again, was just by using CARAVAN, but if we use this other option, then we see a much better fit to the observations. And finally, here we can see at the streamflow recession, so when the streamflow is decreasing after a peak, again, we were over-predicting by a lot, and then we are having a much better fit again here. Here are the median metrics too, so you can compare, but when we were just using CARAVAN, we had an NSE of 0.3, and now we have an NSE of 0.7. We are much closer to 1, that's what we desire. Also, when looking at the means ratio, we see a huge improvement. We were over-predicting by almost 30%, and then now we are just over-predicting by 16%. So that's a huge improvement too. So what are the conclusions for the Uruguayan basins? So CHIRPS and MSWEP still works really good. So the results for the US happen to work for Uruguay too. And it's really close to the to the model that used the full ensemble. So that uses all the precipitation products. MSWEP still is the best option if we just want to use one product. But we saw that including gauge information helps a lot when it's about the peaks specifically. So as takeaways and challenges from this project, the precipitation source matters. The length of these dry periods and the timing of the precipitation is really different between them. MSWEP seems to be the model that works best, at least for the US and for Uruguay. And CHIRPS and MSWEP works really good as an option with just global products during the training process. But when we have local gauges information, we see a really good improvement for the peaks. So what's the challenge now? So these hydrological signatures seems to improve when using gauges because we think that they have key information when it's about the timing of the precipitation. So this is what likely improves our simulations, but we still have to prove that. So our challenge here is maybe we can use some explainable AI methods to formally confirm this and quantify this improvement too. Finally, I want to say thank you to the Science Institute for picking my project for the Data Science and AI Accelerator, to Microsoft AI for Good Lab for providing me with the Azure credits to do this project. Also to Fulbright, I'm a Fulbright scholar, so that's why I'm able to be doing my master's here in the US. And finally, to the Uruguay Institute of Meteorology for the precipitation data, and to the Ministry of Environment for providing the streamflow data. Thank you.